We understood different types of measurement of temperatures, correct? Now let's look into the next part, which is types of expansion. So in this, there are three major types of expansions: linear expansion, area expansion, volume expansion. Alright, so these are the three types of expansions. Look at the figure. See, this is linear, this is area, this is volume expansion. So all the three, if you look at it, one dimension, two dimension, three dimension expansion, correct? Now let's understand what is linear expansion. Now in this one, see the figure. Now here, the length of this particular rod or any material is increasing, isn't it? If the length is increasing, let's call that initial length as L. Alright? Then the expanded or the change in the length, we'll call it as delta L. Now, the change in the length, on what all factors does it depend on? Let's look into that one. First thing, delta L depends on the value of L. That is, delta L is proportional to L. More the length, then more will be the expansion, isn't it? The second parameter is what? Delta L is proportional to delta T. That is the change in temperature. More temperature you are going to increase, more is going to be the increase in the length, isn't it? Combine both of them, you get delta L proportional to L into delta T. Remove the proportionality, introduce a constant. We get delta L is equal to alpha L into delta T. Now that alpha is called as coefficient of linear expansion. Alright. Now, if you make alpha as the subject of formula, we get alpha is equal to delta L by L into delta T. Correct? So that coefficient of linear expansion alpha can be called as the change in the length by original length into the change in temperature. In the sense, suppose if I'm going to increase the temperature by unit temperature, in the sense say 1 degree Celsius. For 1 degree Celsius, what is the change in the length compared to original length? Okay, to give you a practical sense of it, let's say you have 1 meter length iron rod. Okay, 1 meter length. Now, let's say you are going to increase the temperature by 1 degree Celsius. So, from 1 meter, say it increased to 1.05 meter. Now, what is the change? 0.05, correct? So, this is the temperature coefficient for the material. In the sense, for the given length, if I increase the temperature by some degree Celsius or Kelvin or whatever it is, if you increase the temperature, what is the change in the length? Okay, that is alpha. Now, what if we have two different temperatures and two different lengths? That is, suppose if you have L1 and L2 types, then you'll get L2 is equal to L1 into 1 plus alpha into T2 minus T1. This is the change in the length, or you can also call it as the increase in the length. Alright. Now, alpha, the SI unit is per Kelvin, but generally we can call it as per degree Celsius or per Kelvin. This is linear expansion. Now, the second part is what? Area expansion. The next type of expansion is what? Surface expansion. Look at the figure. Now, let the original area be A. See here, what are we doing? We are expanding the area by giving the temperature, isn't it? That means it's a 2D expansion. Now, that expansion in the area, we'll call it as delta A. Fine. Now, what all factors that does that delta A depend on? The first thing is the area. That means delta A is proportional to A. Alright. The second parameter is the temperature. So, delta A is proportional to delta T. Now, combine both of them. We have delta A proportional to A into delta T. Now, to remove the proportionality, introduce a constant. We call this as beta. So, delta A is equal to beta A into delta T. So, what is beta? Beta is equal to delta A by A into delta T. That means the area coefficient of expansion, or you can also call it as coefficient of area expansion. This beta is equal to the change in the area by the original area times the change in the temperature. Okay. Now, just like the previous example of 1 meter length, I'll take 1 square meter area. Okay, 1 square meter area, you increase it by, let's say, 1 degree Celsius. Okay, say the area expanded to 1.05 meter square. Okay, so by how much the area is increasing? To understand that, we call this beta, the coefficient of area expansion. Suppose if you have two areas at two different temperatures, then you have A2 is equal to A1 into 1 plus beta into T2 minus T1. Okay, here also the unit is going to be per degree Celsius or per Kelvin. It's pretty much the same. Alright. The third type of expansion is what? Volume expansion or volumetric expansion. The same image here, the volume is increasing, isn't it? Now, guys, the same logic we have to apply. The initial volume is V. Once you provide temperature or once you provide heat energy, the volume is going to increase. That increase in the volume or change in the volume, we can call it as delta V. And delta V is proportional to V. More the initial volume, more is the expansion. And also, delta V is proportional to delta T. So we have delta V proportional to V into delta T, or delta V is equal to gamma V into delta T. Gamma is called as coefficient of volume expansion. So now what we have, gamma is equal to delta V by V into delta T, or change in the volume by original volume into change in temperature. Clear? So this is for volume. Now again, if you have two different volumes at two different temperatures, then you have V2 is equal to V1 into 1 plus gamma into T2 minus T1, which is pretty much the same thing what you have for linear area and volume, isn't it? Here also, the unit what we use is per degree Celsius or per Kelvin. Fair enough? So, to understand, alpha is linear, beta is area, and gamma is for volume. Okay, these are the coefficients of expansions. Now, there is another type of expansion, and this is very, very specific only to water. This is called as anomalous expansion of water. Now, anomalous meaning what? There is some sort of difference, correct? So, anomaly. There's some sort of, there is a small difference here. Like what every material or what every object goes through, water slightly changes. So, some sort of an anomaly is there. Now, what exactly happens in anomalous expansion of water is that, look at the graph here. See, generally what happens? As you increase the temperature, volume also should increase, correct? But if you look at this one, from 0 to 4 degrees Celsius, the volume reduces, isn't it? And since the volume reduces, what's happening here? The pressure also changes. The temperature also changes. Okay, because of that, we have the relation between the volume and temperature, which you guys will understand this later. As the volume reduces, the temperature changes. Okay, and after 4 degree, look at this one, the volume and temperature, they're going proportionally. In the sense, from that 0 to 4 degrees there, right? That is the anomaly in only seen in water, not in any other substance. Okay, so at 4 degrees Celsius, the water is going to have, look at the graph, it's going to have the least volume, correct? It's going to have the least volume and then finally it will start to increase. Now, this is the reason why even though the top part of the water is frozen in a lake or something, the bottom part is going to be still liquid in nature. That's why the marine animals can live. Okay, so anomalous expansion of water, this is a different type of expansion again with respect to temperature. From 0 to 4, the volume reduces even though temperature is increasing. After 4 degrees Celsius, the volume increases as you increase the temperature. Understood? So we learned about 4 types of expansion now. The first three are very important, which is linear, alpha, area, beta, volume is gamma. Then the fourth type is the anomalous expansion and only for water. So in this anomalous expansion, 0 to 4 degrees Celsius, the volume reduces. After 4 degree, the volume is going to increase. All right. So these are the types of expansions what we see when the temperature is increased or decreased for different types of materials.